Guys. How you guys doing? All right. So today we're going to finish up talking about chapter 2.3. We'll probably spend, most of the period talking about 2.3. I'd like to spend the first few minutes before we actually jump into 2.3 talking about some problems on the quiz that we just took on Thursday. I saw like sort of a consistent, most of you got like the right answers and got the right idea on things, but I saw some consistent confusion about, just a minute, got some consistent confusion about inflection points, okay, and how we talk about concave up, concave down stuff. So I want to talk about the quiz just for a little bit, and then if we have time at the end of class, okay, after talking about 2.3, then I'll answer any questions that you guys have on homework. Remember, this Thursday, it's 2.1, 2.2, 2.3 that's due, and that's going to be the basis for our quiz on Thursday. So keep that in mind in terms of like what's coming up, coming down the pipeline here. All right, so the quiz, most of you guys got this question 2, the right idea on a lot of things. And when we did this, I took things, if they were like reasonable, like I could kind of tell that, you were looking at things correctly. I also, I know the graph didn't have arrows on here, so if you just wrote like, to 5, or if you went off to 6, I took that as well. Typically we tend to think of these functions going forever, but if you just wrote the boundary points, that's fine. The part that got confusing for some people was where the second derivative is positive and negative, right? That's describing places where we have concave up and concave down. Now, the way we describe concavity in a function is that we look at intervals of x where the concavity is happening. So it's concave up on this interval of x to that interval of x. Like, this is how we're defining it. These values here are going to be our inflection points, okay? Now, I realize this graph isn't great, but what happens is our concavity comes down, right? You can see how it's concave up, and then it shifts to concave down, and then it shifts back to concave up again on our curve, okay? But here, we've got our inflection points, like right around here to here, okay? But somewhere around the middle point, or somewhere around in between here and here, we have a concavity change. We have an inflection point change. So we're looking, some of you guys gave me, this point here, like our, we're across the axis, and that's not necessarily true. Some of you gave me the critical points as where our concavity is changing, and that's definitely not true. So here it looks like right around at this point here, I can kind of start to kind of see the graph. And I know we're just interpolating this graph right here, but somewhere around -2 and somewhere around, say, +2, I'm looking at an inflection point here. Okay, so I'm looking at, it's going to be concave up. And I said from -infinity, but I also took it if you said -6. -infinity up to -2 was a concave up, but also it's concave up from, say, 2 to +infinity, okay? These boundaries here need to line up because we're switching our concavity along the same points, right? The inflection point is where the concavity changes. So our concavity changes from up to down right here, right at the same spot, right where we end our concave up is where we start our concave down. So where I end is where I'm going to start. All right, so I go from -2 to +2, so where I end here is where I'm going to start at this point here. So those things have to line up definitely. But where I'm looking for my concave changes are my inflection points. Not necessarily where it crosses the x-axis, and it's definitely not at our critical points, unless we're dealing with a special case where our critical point is actually an inflection point because it isn't a place where our tangent line is equal to 0. That usually happens on our cubic or odd exponents. All right, so the one that had some people confused was question 3. So this is, I want to talk about this for a minute. So this is quiz 3, question 3. So on this one, we had the function, let me write that down. We had the function f of x equals 3x cubed plus 2x squared minus 5x plus 1. All right. So I graphed this one out. I graphed this out. So 3x cubed plus 2x squared minus 5x plus 1. And I graphed, right? I use our graphing calculators are allowed on exams in this class, so you're welcome to use your graphing calculator to help you solve. So this is going to look, we know like our y-intercept is here, it's going to go something like this. Okay, so here's my function, and I got that from my calculator. I'm going to use my calculator to help me solve for things. The first question is our y-intercept. Okay, so y-intercept is right where x is equal to 0. So I'm just basically plugging in everywhere I see an x, I plug in 0, and I get that's equal to 1. Yeah, this is a coordinate. 0, 1 is my y-intercept. If you just wrote it was equal to 1, I took that too, but you should know it's a coordinate. Our x-intercepts, we've got 1, 2, 3. I can see them on my graph. I've got 3 x-intercepts. The x-intercept is the same thing as a 0, a root, a solution. It's all synonymous with x-intercept. It's where our function crosses through the x-axis. It gives us y equals 0. It's a solution to our function. And for that, I just did it by my calculator, by the graph, right? So I plugged this in. I said, you know, this is going to be 3x cubed plus 2x squared minus 5x plus 1 equals 0, and I solved for x equals. Some of you tried to do some really nice fancy factoring, but be very careful about that because we're not judging your algebra at this point, we're judging your calculus. So you're welcome to use your graphing calculator to get these points here. So my graphing calculator, I've got a 0 function. I can just plug it in, and then I can tell it where to click, and it's gonna tell me my 0 crossings. It's a little cumbersome on my old calculator. I had to tell it 3 times. But I'll get these different values here. So my x-intercepts here are 0.228, 0. I've got 0.842, 0, and minus 1.74, 0. The 4. Some of you guys also keep in mind we're usually going about 3 decimal places out, sometimes 4 decimal places out in terms of how far out and past the decimal place. I only went 2 here. Some of you guys just gave me 0.2 on here. You have to be really careful. That's not going to be enough fine grain on your answer. So make sure you're going out at least 3, maybe even 2 to 3 places after your decimal when you're giving these solutions. Okay, so these are x-intercepts, they're coordinates as well. All right, so now we're getting into the calculus part. So this was all just like algebra stuff, right? So the critical points, remember, critical points are where I take my first derivative, set it equal to 0, and I solve for x, right? So what I'm doing for here, I'm going to take this function here, I'm going to take my first derivative. So my first derivative equals 0 is going to be 9x squared. For this stuff here, for chapter 1.5, 1.6, you can use the power rule, absolutely. Now, what you'll want to be doing is looking forward on quizzes and tests and stuff. When I say use the definition of the derivative, you must do the limit. Limit is h goes to 0. I'm taking, the slopes of the secant lines. If I don't say use the definition of the derivative, you're free to use whatever method. Okay, power rule is going to be the quickest way to get there. So for this stuff, we're going to do power rule plus 4x minus 5. Okay, now this is a quadratic. Again, I can plug this into my graph, 9x squared plus 4x minus 5. I can graph it out. I expect it to be a parabola, right? I've got these 2 x values where it crosses the axis, so I know I'm going to have at least 2 critical points, possibly, that I need to check for. I can use my graphing calculator to help me with that. I can also use the quadratic formula, minus b plus or minus square root b squared minus 4ac all over 2a, and then solve for my x values. At that point, I don't care. Some of you guys tried to do factoring, but you factored it wrong. Please, if you're going to factor, you've got these 2 binomials, just do a quick FOIL, do a quick check to make sure that when you multiply things out that you get back to where you are. There's nothing so frustrating as getting all the calculus right, but the algebra wrong. It's really heartbreaking. So anyway, here, when we do this, we get our critical values, our critical points. The x values that I'm going to get are going to be -1 and 0.55. Okay, these are x values, x equals -1, x equals 0.55. Okay, so critical points are x values, right? Now, my critical values, these are y values, right? So I take my critical point and I plug it into my function. Plug it into your derivative, you'll get 0, hopefully. So I'm going to plug these into my function, f of 0.55, to find out what the y, corresponding y values are, right? Critical value is a y, critical point is an x. Okay, so the critical values that I get, the 5, and this one's equal to minus 0.65. So you could write these as coordinates, 0.55 minus 0.65. However, it's fine. You know, these here are your critical values. Okay, so critical values. Now we're going to apply our critical values. We say places where our function is increasing and decreasing. Right now, this point here, we're doing our first derivative test. Right, I'm checking places on either side of my critical point. So I'm going to check values of x. I'm going to check to see what's my slope like. And I don't know, do we have 3 new homework? Yes, we do. We have 2.1, 2.2, 2.3. We have homework due on Thursday. Anyway, increasing, decreasing. So I'm doing my first derivative test. So I'm checking to see on values that are slightly less, slightly greater than each critical point. And I'm checking to see it as my, you know, does my first derivative change sign, right? So it's going to be, if the first derivative is positive, my function's increasing along that interval. If it's negative, my function is decreasing along that interval. Okay, so I'm doing my first derivative test at this point here. I could also do my second derivative test and identify min and max, and then from how I know that I have a min or a max, if it's a minimum, then I'm decreasing and then increasing. So you have to interpolate. First derivative test is going to tell you exactly where things are increasing or decreasing. These are intervals of x value. So my increasing x intervals, and these include my critical points, right? So this is where they're increasing. So minus infinity to -1 and 0.55 to positive infinity. This should line up. It should be consistent with your graph, right? Let's take a look. We'll write this down and then we'll check our graph. So when I do my first derivative test, I'm going to get decreasing from here to here. So when I take a look at my graph, I say, oh, it's increasing. So this is, I said these were critical points. This is -1, this is 0.55. I said it's increasing from minus infinity up to my x value, x equals -1. This looks like a coordinate here, but it's not, right? This looks like a coordinate. This one really looks like a coordinate. This is an interval of x, okay? So when x is all the way up from minus infinity, so when x comes into minus infinity, my function itself is increasing up until this point right here. And then it decreases, right, from -1 to 0.55, and then it increases again from 0.55 to positive infinity. So the critical points are going to tell us places, hopefully, where our first derivative test, where our function is increasing or decreasing. So that's our first derivative test. Concavity now deals with inflection points. This is the part that a lot of people kind of like, I could see maybe there was some confusion, which is why I'm spending time on it now. So inflection points means I take my second derivative and I set it equal to 0 and I solve for x. That's going to give me where I go from concave up to concave down. That inflection point is where my second derivative is equal to 0. Okay, so that means, right, I'm taking this function. Here's just my first derivative. I'm taking the derivative of that. Let's go ahead and do that. So I'm going to take my second derivative. Right, so my second derivative says 18x plus 4, and I need to set that equal to 0, right? So I'm doing my power rule. 9 times 2, I subtract 1 from the 2, plus, right, plus 4, and then the 5 drops off because it's a constant term. So now I need to solve for x. Be careful, some of you guys did this, you know, a little bit crazy. So this is 18x equals -4, divide by 18. So x equals -4 over 18. It's negative, which I moved as a decimal, so I called it minus 0.22. Okay. Some of you left it as a fraction, which was totally fine. I can figure it out. So now I have an inflection point. This is my inflection point, which it makes sense that I have only one, because look, I have concave down, concave up, so my inflection point is right around here, minus 0.22. Minus 0.22. Okay, so it's changing from concave down to concave up. How do I test that? I can do my second derivative test to check for max or min. I can put values into my second derivative to see if things are positive or negative. Okay, so depending on whether things on this side are positive or negative, it's going to tell me whether or not I'm concave down or concave up. Okay, but when I talk about intervals of concavity, I'm talking about intervals of x leading up to my inflection point. So intervals where our function is concave up, right? I'm going to go from minus 0.22 to positive infinity, and then concave down, right? I'm going to go from minus infinity to minus 0.22. So this is my inflection point, right? It has nothing to do with my critical point, unless it happens that my critical point is not actually a critical point, but an inflection point. And that can happen on a cubic. Okay, we see that on x cubed, right? If I take the derivative of x cubed, I get 3x squared. It looks like x equals 0 is a critical point, but there's no sign change. The function's continuously increasing. I take the second derivative, I get x equals 0 as an inflection point, and sure enough, I actually have an inflection point at x equals 0. So it's kind of a trick. It looks like it should be a critical point, but it's not. It's actually an inflection point. But here we have different values for our inflection points and our critical points. Okay, the critical points are going to define max and min, and our inflection point is going to tell us where we're changing from concave up to concave down, or vice versa. Okay. Anyway, I wanted to cover this because there was some confusion on the concavity. Concavity, intervals of concavity deal with intervals using our inflection point. Okay. And maybe I was beating a dead horse on this one, but I felt like it was important that we cover that because I did see some confusion on it. Alrighty. Okay. If you guys have further questions on the quiz, please contact me in office hours, and then we can talk about it. Okay. All right. So with that said, let's talk about our chapter 2.3. So we're continuing on with chapter 2.3. We have a couple more ideas to cover with regards to the chain rule, and then we're going to get into inverse functions. Okay, so we'll talk about, these are theorems. So this is a general power rule and exponential rule. We've covered these in bits and pieces, okay, but now we're really going to call your attention to it. So let's first off say we've got this function g of x, and it's differentiable. Okay, so now watch. If I say dx, I'm trying to find the derivative. I've got my g of x raised to some power, right? N is my exponent. N is just a number, right? I'm raising. We do this all the time when we say x squared plus 1, take the square root of that, right? X squared plus 1 raised to the 1/2 power. So that 1/2 is just a number, right? It's just an exponent. N is your exponent. And we're going to use the power rule. Power rule followed by the chain rule, right? Because I got to take the derivative of the function inside. So when I go to take this derivative, what this looks like is I do the power rule part. So I bring my exponent down out front, and I've got my g of x raised to the n minus 1. I have to subtract from my exponent. And now I need to do my chain rule. Right, so this here is the power rule. And this here is our chain rule. And we'll do examples of chain rule where we nest it a couple times, okay? But you're gonna, like if this is g of f of x, I'm gonna keep going farther and farther down until I hit all of the functions that are included, okay? So power rule, when I'm raising some function to an exponent value. Okay, that's gonna look like, I'm looking at my lecture examples page for 2.3. I'm looking at example 5. So this here is our g of x, that x squared plus 7x plus 2. Okay. Now this here is my n. My n is equal to minus 1/3. Okay, it's just a number, right? It's an exponent. So now if I want to find my derivative, y prime, I'm going to do the power rule first, and then I'll do the chain rule. Right, because I have a function on the inside I have to take care of. So my power rule says bring my exponent down out front, minus 1/3. X squared plus 7x plus 2. I have to subtract minus 1/3, third minus 1. Subtract 1 from that. And now I need to take the chain rule, the derivative of what's inside. That's 2x plus 7. Okay, power rule, chain rule. And then we'll make it look nice, right? We'll kind of clean up. Technically we're done, but although you should put this into an actual number. So this is going to be minus 1/3. We typically do 2x plus 7. And then we put this big conglomerate on the outside, plus 7x plus 2, minus 1/3 minus 1, that's minus 4/3. That's a 4. Okay, and then you're done. You can put it in the denominator, you can put it to the 4th, take the cube root. It doesn't matter. Don't go hog wild on it because you're more likely to make a mistake when you try to, combine terms and whatever. Just leave it. Okay, so 4/3 there. Okay, now, you guys have that? Okay, now this is different from an exponential. So I'm going to write exponential function. We'll talk specifically first about e to the x or e to some function, and then we'll talk about it in terms of a generic base. Okay, so the first thing, I'm going to take the derivative e to the g of x. Remember, g of x is our differentiable function. Now this is different, right? Because my function is in the exponent. Okay, so function in the exponent, and the base of the exponential, in this case, is e. Remember, e is our transcendental number. Base of the exponential, right, is a number. Okay, so what I'm going to write in red is you can't use the power rule. You cannot use power rule. So power rule. Okay, you can't use the power rule on an exponential. Right? I see it all the time, but it's wrong. So be really careful. So when we want to take e dx of e to the g of x, how we do this is this. I repeat my exponential. Oh, sorry, g of x. Then I do the chain rule. And then you take the natural log of the base. Oops, that's a e. E. Natural log of e is equal to 1. We don't write it. I'm writing it here so that you can see this is our general form for taking a derivative of an exponential function, generally speaking. Base equals b, right? So b is some number, right? So b, in this case, b was equal to e, which is 2.718, so on and so forth, right? So this is dx e to the g of x, right? So how we would handle that, right? You can't do the power rule on this because this is a number, this is a function. My functions in the exponent have to do something special. So I repeat my exponential, I do the chain rule, and then I take the natural log of my base. Okay, we do it with our e to the x, but we don't see it because that's equal to 1. But here it's some number, right? I'll just do a really quick, super quick example here just so you can see. I will do an example with e to the x in a minute. But let's say I had, I take the derivative, 2 raised to the x squared. Okay. So now, look, my base is, I can't do the power rule. How am I going to do the power rule? I've got this exponential 2 to the x squared. So to take this derivative, what I'm going to do is I repeat 2 to the x squared times my chain rule, 2x, times the natural log of my base. I'll put this in parentheses so that you know it's a block. I cannot combine this 2x with that 2, right? Because this 2 is locked into as a base of an exponent. It's being raised to a power. I can't multiply it, right? This is a function. So now the most I can do is I can actually, ln of 2 is just a number. I can, you know, multiply it out. I can multiply ln of 2 times 2 ln of 2 times x times, I'll put this in parentheses, x squared. And that's our derivative of a general exponential function. It's the form. You cannot do the power rule. And we're going to try to trick you on that. So make sure you're aware, right, when you're dealing with a polynomial, which is x raised to some number, okay, or an exponential, which is some number raised to the x. Okay. Example 5, part B is an exponential function, right? So I want to take my derivative here. So what I do is I repeat e to the cosine of t times I do the chain rule. Derivative of cosine is minus the sine of t. Okay, and I'll put the natural log of e. So we're in the habit of looking at it. We're in the habit of looking at it. Now let's clean it up. I put this in parentheses so I'm not confused into thinking it's a subtraction. So this becomes minus the sine of t e to the cosine of t, and I'm going to drop the ln of t. Okay. 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 Be very careful. People always fall into the trap and they take the power rule with an exponential, and it's wrong. I have to take off points. Okay. So you pull this out as a special theorem, the shifting and scaling. You do this as part of the chain rule always, but I'm going to give you just what the theorem is. It's called the shifting and scaling rule. Okay, so our function f of x is differentiable. Okay, and then we have constant terms, a and b. Okay, so now I want to take the derivative, dx of f of ax plus b. Okay, we've done this already with the chain rule. Okay, right. So I'm going to say this is going to be my, here's ax plus b. I take that derivative of the outside function, and then I do the chain rule. So the derivative here, sorry, it's a b. The derivative of here, right, is just equal to k. So let's write down, this is our power rule. And this is our chain rule. We call it shifting and scaling because shifting we think about in terms of trig functions where this plus pi over 4 on our sine function is what we call phase shift. We're shifting our whole function over by pi over 4. Now, so when I want to go take the derivative, but you guys just approach it like you would with the chain rule normally, okay? So the derivative, sine of 2x plus 4. So I take the derivative of the outside function. I take the derivative, this is like sine of u, or my u is equal to 2x plus pi over 4. My du is equal to 2, right? Pi over 4 is just a constant term, drops off, right? And doing this derivative with respect to x, so my du is that, so sine of u, I want to take that derivative, right? So that's going to be equal to du sine of u times du, right? So we're going to do this. Derivative of the sine is our cosine. I repeat what's inside, that doesn't change. Okay, now I do my chain rule times 2. Okay, again, I'm going to bring the 2 out front, 2 cosine 2x plus pi over 4. That helps me remember that the 2 is a multiplier of my outside function. Okay, you may not ever multiply this 2 by the stuff inside. Whoops, wrong. Okay, don't ever multiply this 2 by the stuff inside. Okay, this is like locked in as part of our parameter for the cosine function. Okay, so that's our derivative there. Okay, so that's our shifting part. This, right, we're just going to approach it like we would a regular chain rule. Okay, so I first do the power rule, right, because I've got this exponent, and then the chain rule, because I have a function on the inside. Okay, so my power rule says I bring my exponent down, 9x minus 2, I decrease by 1, and then I take the derivative of what's inside, which is just equal to 9. I multiply the 9 and the 5, they're both constants. and then you're done. Right, that's it. Okay, but we're throwing it under the same this shifting and scaling rule, but it's basically just the chain rule, okay, that we're thinking about here. Okay. All right. Our next example, this one, example 7, is going to use the chain rule twice. So chain rule twice. Okay, and the reason is because I've got a nested function inside of a function, right? So we need to go down into all those functions on the inside. So let's first rewrite this in terms of exponents, because I will have to do my power rule. Half the 1/2. Okay, so now I could assign this two variables, two substitution variables, where I've got a u on the inside and then maybe a v on this bigger function here. I just did the u on the inside. So I'm going to say my u is equal to x squared plus 1. So my du is equal to 2x. Okay, so notice how I didn't say x squared plus 1 to the 1/2. I just did 2x. Okay, so then when I want to go to think about what's my derivative of this function here, I'm going to substitute in my u. So I'm going to go 1 plus u to the 1/2 to the 1/2. Okay, so when I go to take that derivative, first I do the power rule part of it. I'll give myself some room. So the power rule part of it says bring down the 1/2, 1 plus u to the 1/2, 1/2 minus 1, that's minus 1/2. Now I have to do the du, right? But this du, I have to do the power rule here. So let's do this. So this is multiplied by the power rule here. So I'm going to go 1/2 u to the minus 1/2 times my du, which is going to be, I'll write du here. And now we have to substitute everything back. So substitute. Okay, so I'm going to substitute. So 1/2, 1 plus, so u was x squared plus 1. X squared plus 1 to the 1/2 raised to the minus 1/2 times 1/2 x squared plus 1 to the minus 1/2 times du, 2x. Okay, now technically speaking, you're done, right? But we're going to clean it up. So I have a 1/2 times a 2, so they cancel each other out. So I'm left with this 1/2 times x, 1/2 x, 1 plus x squared plus 1 to the 1/2 minus 1/2 times this bit here, x squared plus 1 to the minus 1/2. Okay, and that's it. Technically, I could have left it like this, but I kind of cleaned it up a little bit. Don't worry about like putting things in the denominator or multiplying things through. Leave it. Okay, you're done. Okay, but I had to nest. I had to think about it. How I assigned this as u was arbitrary. You didn't even have to do that, but I find sometimes it can be helpful to do substitution of variables so I can keep track of what it is I'm trying to do. Okay. I'll let you guys finish writing that. Then we'll go into the next part of chapter 2.3. You all set? Okay. So this is our inverse functions. We'll talk about inverse functions. There's a whole class of study that deals with inverse functions. They're pretty important in terms of what we're trying to do. So we need to be able to take the derivative of our inverse function too. So let's think about our function. We've got a function f of x. Now I can take my inverse. Remember, we write it as f to the minus 1. Now be careful. I've got an x to the minus 1 button on my calculator. That means taking the reciprocal. This is an inverse function. Remember how we did that? We switched the x and y and then solved for y. But the switching of the x and y means we switch domain and range, so that my domain and range for my function this becomes my range, and this becomes my domain of my inverse, right? So my domain and range get switched, which is what we mean when we say switch the x and the y and solve for y. So when we did this stuff in Algebra 2 or pre-calc, depending on when you would have had it, we focus on functions where we could actually solve for y. Okay, but some functions are going to be too hard to actually solve for y, so we need a better way to think about how I'm going to take the derivative of this inverse function, right? That's our goal. So I'm going to first draw out a picture of what our inverse function looks like, and then we'll keep referencing this picture when we talk about stuff. So let's draw out our picture. My x-axis, here's my y. I'm just going to draw some random, here's my random f of x, right? That's my function. Now remember, our inverse functions have a graphical symmetry to the line y equals x, right? So my function here, my inverse function, I'll try to make it look as much like that as I can. What's up? This is my inverse. Okay, so I've got my inverse function, I've got y equals x, and I've got my function. Now, ultimately, remember, we're doing calculus, so I'm going to start thinking about like a secant line. So I've got a point AB, and I have a point CD. Okay, now I'm switching my x and y, so there's a corresponding point here. This is D comma C. And there's a corresponding point here that's B comma A. So keep that in mind, right? Because we're going to come back to those points when we talk about the slopes of our tangent line. So let's do our derivative of our inverse. So this is a theorem. A lot of words here. I'm going to write the words out. We're going to decode it, and then we'll go through some examples. So derivative of our inverse. Okay, so first off, I have to make some assumptions about my function. So we're going to assume that our function that we're starting with is differentiable. And that it has an inverse that's one-to-one. So, you know, there's a corresponding point. Our inverse is a function, and it's one-to-one with its inverse, minus 1 of x, which we'll call, for ease, g of x. Okay, so this is our inverse of our function we're going to call g of x. Okay, so now we've got some point. If some value, it's like x equals b, belongs to the domain of our g of x, and watch this, my derivative of my function evaluated at g of b doesn't equal to 0. This is what we're trying to do. So b belongs to the input, the domain of my g of x, which means b is in the range of my function. So b is in the domain of our inverse, and g of b is some value equals to some number, right? I can evaluate that function. That number I can plug into my derivative. As long as that's not equal to 0, then I can say, watch this, this is our magic trick, g prime of b equals 1 over f prime of g of b. That's why we don't want it to be equal to 0. So I'll put a box around that. Then we're going to go back to our graph so you can see where this comes from, right? Like, why am I saying that? So let's go back to our graph and take a look. So always with our derivatives, right, we're taking our definition of derivative says I've got my secant line, and I'm going to take the limit of that secant line as it approaches some point. So let's say here I've got a secant line between these 2 points here. I'm going to try to over-exaggerate it. So this is line L, I'll call it. And it has slope equals m. Remember y equals mx plus b, our slope was equal to m. And this was, the slope was equal to the change in y over change in x, which the change in y, this is going to be d minus b. So I'm looking at my y points, d minus b all over my change in x, d minus a. Okay, that's the slope of this line here. Now remember, our definition of derivative says I've got the secant line, I'm taking the limit as I approach this point right here. I'm looking for the tangent line here. Okay, so now I'm going to do the same thing here on my inverse function. Let's say I've got a line here. So I've got a line, we'll call it L prime. I know it looks like a derivative, but it's L prime. right? So L prime, and the slope, it's an inverse, so the slope is equal to 1 over m, right? Which is our change in y over change in x. So watch what's going to happen. Change in y. C minus a all over, oops, d minus b. Look, c minus a over d minus b is the reciprocal of my original function slope, right? So that's why we say 1 over m, that's this right here. So that's what we're working with, okay? So this is equal to g prime at b, and then this is equal to f prime at a, okay? So we're looking at how are we using our graph. The graph should help you visualize our function, its inverse, the secant line of our function, the secant line of our inverse, okay, how we come up with the slopes, okay, and how they're related, right? I'm looking at my tangent line here, my tangent line there, okay, and I want to be able to come up with a formula, and we need this formula because sometimes our functions, I can't easily find the inverse, right? We're going to do two examples, one where I can find the inverse, pretty straightforward. We're going to do it where I find the inverse and I take that derivative, but I'm also going to use the formula. You're going to see how it's kind of complex. But then it's very helpful when I can't find the inverse and I've got this formula to help me actually find the derivative. All right, so let's jump in. Example 8. Okay, so I'm looking at calculate g prime of x when g of x is the inverse of this function here. Okay, so we're going to do this the old way where I calculate g of x. So I switch x and y and solve for y. Okay, so that means I'm going to say this is equal to y. So what I'm going to do is this. I'm going to go, I'm going to say this is x equals y to the 4th plus 10. Now I need to solve for y. Okay, this is my process of finding the inverse. So I'm going to subtract 10. So x minus 10 equals y to the 4th. I have to take the 4th root. And this is all going to be positive because that's how we defined it here. So this would make it 1-to-1. It would make it a function. So then g of x was our inverse of x, which is equal to, right? This is x minus 10 to the 4th root, which I'll write as an exponent. Okay, so that's my g of x. Now my g prime of x, right? I can just take this derivative, okay? Because I've got my function, I can take the derivative. So I'm going to go 1/4 x minus 10 to the 1/4 minus 1 is minus 3/4. And that's my derivative of my inverse function. It's straightforward, right? Because I can actually find my inverse function. It's just, you know, this equation here. Let's do it with our theorem, right? And we'll see how it's working with our theorem. We're going to get the same answer here. Okay, so now we said we've got minus 1. Let me write it again. G of x equals minus 10 to the 4th. Okay, so now my derivative, my function, my derivative of this function here is just going to be 4x cubed. Okay, my derivative evaluated at g of x is equal to 4 g of x cubed. Okay, so by our theorem, I can say g prime of b. I don't know what b is. I'm just using it as a variable. 1 over f prime of g of b. Okay, so if my g of x, my g prime of x is going to equal to 1 over 4 g of x cubed, okay, which then I plug it in and I'm going to get 1 over 4 x minus 10 to the minus 3/4. Okay, so I'm plugging things in. It all looks very confusing, right? We found our inverse for plugging things in. It looks like what we had before. So this is 1/4 x minus, oops, sorry, this is positive, x minus 10 to the minus 3/4. If I put it up here, this is a positive down there. Okay, it looks like I just did a bunch of stuff. I'm kind of all over the map, okay? It's easier if I can actually just take the inverse and take its derivative and evaluate it, okay? Than to try to figure out, okay, what am I trying to do here? Especially if I'm not working with a particular point. Bear with me. You're more likely to see questions like example 9. So example 9, I've got this function f of x equals x plus e to the x. Now, if I do the same method that I did before, I switch the x and the y and I solve for y. Y plus e to the y, how do I solve for y? It's going to be really complicated. So I can't really find my inverse function easily, right? So now I need to use this formula here, where if I want to be able to actually work for that, so let's write down our formula. So my formula says, whoops, sorry, that's a derivative, and we're going to evaluate that at 1. So this is going to become 1 over, it's going to look like that. This is the derivative of my inverse, 1 over the derivative of my function evaluated at the, I'm going to figure out how I'm going to do this, g of 1. If I don't know what the inverse is, how do I calculate g of 1? There's a trick, watch. So now I had to be given a point. If I can't calculate the inverse, I need to know exactly where I want to calculate that tangent line, okay? So now what I know is this. So g of 1 equals something. We don't know that yet. But 1 here is on the domain of the inverse, which means it's on the range of our function, right? Because remember how we switched the domain and the range. Okay, so that means I can say f of x equals 1, x plus e to the x, and then solve for x values that make this true. Okay, sometimes you'll get a value that isn't true, sometimes you'll get multiple values, and you can work it and find out what, because remember you can have multiple tangent lines, right, that are parallel. So now here, what I'm going to do is I'm going to subtract 1. So I'm going to say 0 equals x plus e to the x minus 1. And I need to solve for x. I'm going to do this by the graph. By my graph. So I plug it into my graphing calculator. Right, and I'm going to go x plus, I've got my e to the x button, the x minus 1. Right, I had to solve, I mean, I could say equals 1 and then look for where the two graphs intersect. I find it easier to set this equal to 0, and then I only need one equation. So I'm going to graph it out. This is x plus e to the x minus 1. It looks like this. It looks like I have a solution here. So I'm going to hit my 0 button, right, and it's going to take me, and I'm going to use it to help me find for where that is. So this says when x is equal to 0, right, this is true. So let's just plug it in. So 0 plus e to the 0 minus 1 equals 0. So 0 plus e to the 0 is equal to 1. 1 minus 1 is equal to 0. So x equals 0 makes this true. Okay. So what we're saying is f of 0 equals 1. Okay, domain range, which means in terms of inverse values, g of 1 equals 0. Ha! This, right, I'm going to plug into my derivative. Okay. So now what I get to do is, right, I figured out this value here. This was step 1. I had to figure out what this number is here because I'm going to plug it into my derivative because it's 1 over the derivative evaluated there. So 2, what I'm going to do is this. I have to take the derivative of my function. Go back up to here, taking that derivative. That's 1 plus e to the x. Okay. Now, what I'm going to do is I'm going to say this value here. Well, let's do this step. So we want to do g prime evaluated at 1 is equal to 1 over f prime of g of 1. G of 1 is equal to 0. So this is 1 over f prime. I'm going to substitute in this value here of 0. Okay. F prime of 0, the f prime of 0 is equal to 1 plus e to the 0, which is equal to 1 plus 1, which is equal to 2. So this becomes 1 over 2. I don't even know what the inverse is for my function, but I know what the derivative of my inverse is at a particular point. And that's the important part. Okay. I need to know what point it is because if I can't find the inverse, I'm not even going to bother. But I can then, by taking the derivatives at certain points, I can come up with a feeling for what my inverse function is going to look like. Okay. There's always some question like this on the midterm and on the final. Okay, so it's open book. we do these things that are open book, so you'll be able to remember what your formula is, right? Your formula for taking the derivative of this here, right? This is your formula. Which will be, you'll need to make sure that you have it committed to memory by the time you get to, Calc 2, Calc 3. Okay? All right. So we have some other things that we need to just throw out there. In terms of concepts, we're going to derive our inverse sine, inverse cosine, inverse tangent functions later in a later chapter section, but I'm just throwing them out there for you to have now. So our derivatives of our inverse trig functions. Okay, so we can call these arc sine, arc cosine, arc tangent. I don't care, arc tangent, arc sine, or cosine, you can call it that, or you can write it with a -1. Either one, I mean, I understand that they're synonymous, so it's okay, whichever one you want to use. So I'm going to take the derivative of my inverse sine function, my arc sine function, and my derivative is going to be 1 minus x squared square rooted. Like I said, we're going to derive the geometry on this. Like, where did this come from? We're going to talk about that in a later chapter section. Okay, so my inverse sine, we're going to do it for cosine. This one comes up a lot in Calc 2, so make sure, because you'll be asked to take the integral of this. You'll need to be able to recognize that it's the inverse sine. Also for tangent, cotangent. So tangent minus, positive 1 all over x squared plus 1. That's a squared. Okay. Our cotangent function, that's our negative. Okay. And then likewise for our secant and cosecant. Oops. Secant -1. Cosecant. Right, these things are phase shifted, which is why they're negatives. X. You know what I mean by phase shifted? So tangent is, to get to tangent to cotangent, it's shifted by 90 degrees, right? Like the sine and the cosine are shifted by 90 degrees. Okay, but like I said, these, we're going to do the geometry on these later. So you can see it's sine and tangent. These two show up a lot in Calc 2, right? Because we go to take the integral of these functions here, and you need to be able to recognize them. I'm putting these out here for you now. We'll go over the geometry of them in a later chapter, so don't sweat it if it looks like, where'd those numbers come from? But by Calc 2, you'll need to have these two in particular memorized, because you're going to need them to be able to do the integrals. Okay. And that essentially wraps up chapter 2.3. And then I'm open to answering questions on homework problems. I'll scan in these lecture examples and I'll post them later today so you guys can have them. And then when we meet up again on Wednesday, we'll start chapter 2.4. Okay. Any homework questions? If you guys don't have homework questions, we'll just end a little bit early. More questions. 2.1, 2.2, 2.3 are all due on Thursday. Those are the basis for our quiz. You can ask them in office hours too if you want. Oh, let's see. Someone's asking a question. 2.1, number 18, 2.3. Okay, let me get out my homeworks. Give me a sec to get my out. It looks like, what is 18? Did I think I crossed off 18. Let me just look at I forget what 18 looks like. I think Give me just a second. Let me get the homework out. So 2.1. Degree of polynomial, the largest part of x that appears with the non-zero coefficient of the polynomial. Yeah, so I wouldn't worry about that one. It's more, you can skip 18, it's fine. You guys can skip it. It's more like a thought problem. You know, when I post solutions for it, then I'll post for that one too. But it's more like a thought problem on that. It's kind of like saying if you've got any kind of polynomial with coefficients, you know, generically speaking, a sub k. What can you see about the nth derivative? The nth derivative is going to have nth derivative of the nth degree polynomial. It's going to be n times a sub n x to the n minus 1, basically. So if I have some kind of like a, let's see, hang on, let me get back to my window here. If this is all showing up on the graph. So if I have got a polynomial, so it's a1 x to the 1, oh, this is plus a sub 0, plus a sub 2, x to the 2, plus so on and so forth, plus a sub n, x to the n, right? And I go to take the nth derivative, right? It's going to have all of these terms here, so it'll be like in the form of a1 plus 2a2, x to the first, plus so on and so forth. And then my last term will be n, a sub n, x to the n minus 1. So this will be my highest degree term. N minus 1 is the highest degree term. And then the same thing if I do the n plus first derivative, right? The next one above that will be n plus 1, a sub n plus 1, x to the n plus 1 minus 1 becomes x to the n. So my highest degree term will be 1 less than the derivative that we're taking, essentially. It's sort of like a thought problem. You don't have to worry about number 18. You know, if you leave it blank, that's fine. It's just kind of getting you to think about polynomials in terms of general forms. Nth derivatives are things that we take in calculus 2, because we start thinking about how do I represent a complex function as a polynomial that has an infinite number of terms or has an n number of terms, like if I want to specify where I'm going to cut off. So we're kind of starting you thinking about these, you know, like longer stream polynomials, but I wouldn't worry about it. Let's see, 2.3. 2.3. Oh yeah, so this is chapter 2.3, question 22. So we want to know where's our second derivative, oops, equals 0, right? And we're given our function ax plus b raised to the 10th power, and we say a does not equal to 0, because otherwise if a equals 0, our chain rule makes, it's just a constant term. So then now my first derivative is I'm gonna do the power rule, 10 ax plus b to the 9th, right, because I subtract 1, and then I do the chain rule times a, right? And then so this becomes 10a ax plus b to the 9th. That's my first derivative. Now I want to take the second derivative of that, right? So my second derivative is I've got 10a, that's my coefficient from before, times my exponent, ax plus b, and I subtract 1, and then I take my chain rule again. Okay, so let's multiply this through. So this is equal to 90 a times a squared. A is just a number, right? It's not like a variable. Ax plus b to the 8th power, and I have to set that equal to 0. Okay, so then basically what happens is I divide through. This is just a number, remember. A equals some number, right? Okay, so basically what happens is, right, I'm taking the 8th root of 0, so I get ax plus b equals 0, right? I solve for x is equal to minus b over a. That's it. And 45. Yeah, 45 is a really long one. Can I do this? What I'd like to do for 45, it took me, you know, like a page and a half to do it. Why don't I scan in my solution for 45 and then upload it? Just because I can't hold you longer than that. So let me write that down for myself. So chapter 2.3, question 45. And upload. Okay, so you guys take a look for that later today. I'll put that up on our Canvas page. Okay, and I'm only waiting because it's going to take a while to work it through and we don't have time. If you wanted to ask me in office hours, we can go through it in detail, but we don't have time to go through it that quick. Okay, all right, you guys. I can't hold you past time, so have a great day, and I'll see you on Wednesday. I have office hours today, so feel free to come by and ask questions. Okay, bye.
Thank you.
Thank you.
Easy. Take care.